All right, this is Chemistry26ABlake, or Chem26ABlake, probably what it'll be. And last week was week 2.5, this is week 2.6, obviously. We were going back to the beginning of chapter 8, so we were all the way through the Lewis structures, and if you viewed that video, there was a few minutes of this on here. We're talking about why atoms bond. They're trying to get 8 valence electrons. We'll look at organic chemistry about, something, and we saw this was the expanded expanded octets, that some things could have 10 or 12, and other things may only use 6 or 4 or 2. But most of the time they're trying to get 8 valence electrons, or however many it is they need, and that's why they're bonding, and that's why they're sharing in a covalent bond. And we've been talking about ionic bonds all last chapter. Now we're talking about Lewis structures, that sort of thing, sharing. This chapter's on molecules. Chapter 7 was on ionic compounds. This one is on covalent compounds. Organic chemistry is all about the organic or covalent bonds. Okay, we were talking about if 2 atoms are close to one another on the periodic table, especially if they're nonmetals, they're likely to covalently bond. By the way, if they're close to one another on the metal side of the table, they're just going to make an alloy. But if they're 2 nonmetals, so I need to add this in there. I'll see that it's ugly written, and I'll go fix it later. So maybe that word should be nonmetals. Okay, when 2 nonmetal atoms, let's do it this way. When 2 nonmetal atoms are close to one another on the period. 2 metals are just going to metallic bond and you'll have an alloy. If they're 2 nonmetals, they will actually covalently bond. They have similar electronegativities. Oh, there it says, most covalent bonds occur between nonmetals. Okay, so there are diatomic metals or molecules N2, O2, H2, F2, Cl2, Br2, and I2. I want to show you where these are on the periodic table. I think I can do it here. Here. Here I go. I forget what I was doing though. That's the bad thing. Oh, the double bonds. Look, they are H2 and then N2, O2, F2, Cl2, Br2, I2. There's a little L upside down L shaped here. Those are all diatomic. N2, O2, F2, Cl2, Br2, I2. And H2 up here. You need to know those. It's going to make your life simpler. Now, they are diatomic if they are elemental. That doesn't mean every time you see a Cl, you slap a 2 on there, because it has students doing that. Then what? Well, that's because you aren't paying attention to the parameters here. It has to be molecular. It has to be in its elemental form. Okay, so you need to be familiar with double bond, triple bond, single bond. Terms like molecule, diatomic molecule, to a chemical formula. Molecular formula is just the chemical formula of a covalent compound. NaC is a chemical formula for table salt, but that's ionic. It doesn't have a molecular formula. Carbon dioxide has a molecular formula, CO2, because it's a molecule. But it also has the chemical formula, CO2. Okay, this is new. If you have an atom of, let's say, helium, and another atom of helium, it's noble gas, they don't react, and they get close to one another, the electrons in this atom can be attracted to that nucleus, and the electrons in this atom can be attracted to that nucleus. But at the same time, the electrons here and the electrons there are repelling one another, and the electrons here, or the protons here, and the protons here in the nucleus, they're repelling one another. All those interactions happen at the same time. So there are multiple interactions going on between the nuclei of atoms and the electrons in the electron cloud. Not just its own electron cloud, but electron clouds of atoms nearby, whether they're in the same molecule or not. So there are multiple attractions and repulsions. Covalent bonding happens when the combined total is a lower energy and more stable. All right, there's a figure 3 on page 241 for fluorine atoms that is similar to this. I don't even have this book out to look at it, but I did see it earlier today. I would suggest you look at that with your book. It doesn't look like mine, but it's the same concept. And if you are covalently bonding, let's say you have fluorine atoms, and this side is distance, and this side is energy, and remember, if energies are negative, that's more stable, lower energy, and energy has been given off. This graph makes sense if you start out here with your fluorine atoms far away, and they're not interacting, and there's not an energy involved. If you've got a fluorine on one corner of the room and a fluorine on another corner of the room, the energy level between them interacting is 0. But as you begin to bring them together, and you get them real close together, that energy goes down and that's more stable. In other words, they want to be closer together. And then they reach a distance where they're happy being real close together and the energy's low, and they're sharing electrons. Now, if you try to push them too close together and you start to get the nuclei shoving together, and the electrons all on top of one another, it doesn't want that, and the energy get really high, like really high. So there's an optimal distance for them to be apart, sharing electrons. This is one way to look at it. That's one explanation for how covalent bonding works. Now, if you share one pair of electrons, that's a single bond. If you share 2 pairs, that's a double bond. If you share 3 pairs, there's a triple bond, and that's all you're going to get. If you are in the group 17 elements, this one, the halogens, they'll share 1. You get a single bond usually, although we did see that, well, okay, never mind. We didn't see an example of that with the Lewis structures. If you go to the oxygen group, it'll either form 2 single bonds or a double bond, like water, H2O. Because oxygen has 6, it'd like access to 2 more. So if it's bonding with something over here, it's going to give and take. But if it's bonding with something over here, it'll try to share 2 electrons. So it has access to 8. So like H2O. If you're in the group 15, like nitrogen, you're going to form 3 bonds. It could be 3 singles, it could be a triple, it could be a double and a single. I've got a whole bunch of examples of that in here. There's oxygen with a double bond. There's nitrogen with 2 bonds. Oops, that's a crazy example. That's doing something else. Sorry. That's way ahead of you here. Okay, as long as you don't have weird things going on, like I just happened to show you, you gotta have 3 bonds with nitrogen. 1 triple, a double and a single, or 3 singles. Carbon forms 4 bonds. You can have any combination of single, double, triple bonds and get 4 bonds. You could have carbon tetrafluoride has 4 single bonds. Carbon dioxide has 2 double bonds. Hydrogen cyanide has a triple bond and a single bond. Formaldehyde on the carbon has a double bond and 2 single bonds. Okay, now we got to talk about sigma bonds and pi bonds. And here's where I got to pay attention and I don't say something dumb. If you have a single covalent bond, they're going to be sigma bonds. The sigma bond occurs when the pair of shared electrons is in an area between. So here we have water. There's an oxygen. Here's a hydrogen. There's a hydrogen. We have lone pairs of electrons out here occupying space, but there's no atoms connected to them, sharing. But I have oxygen shared an electron with hydrogen right here. Oxygen shared an electron with hydrogen right here. That's a sigma bond. This, I don't know if you can see it, probably not, but this oxygen orbital is like so, and this hydrogen's orbital is like this. They're overlapping right there. That's a sigma bond. They can form when you have an s orbital overlapping, or you have an s orbital with a p orbital. When two p orbitals overlap end to end. I will show you this. So this is for water, methane, ammonia. All of those are sigma bonds. It gets more complicated when you get to the pi bond. Here's another graph. I had this in there last year. It's a little clearer to see. I didn't get it out of the book, but that's how it ended up there. A pair of shared electrons is an area centered between the two. And be careful of centered, but just because it says center doesn't mean it's in the center here. It's between them. It's closer out here in this diagram. When you get multiple bonds, if you have double or triple bonds, you get pi bonds as well as a sigma bond. A double bond has a sigma bond and a pi bond. I don't particularly like this diagram. A triple bond has a sigma bond and two pi bonds. If you look at this carbon in the middle, it's got really 4 bonds. It's making a bond this way, bond to hydrogen there, a bond to hydrogen there, and this is not 2 different bonds, it's 1. I've got a p orbital up here, shared an electron there, p orbital down there, share an electron down there. And you can say, no, wait, you just said no. Okay, remember your p orbital can have a maximum of 2 electrons. So if it's sharing, you've got 1 electron in this p orbital, and you don't know where it's going to be, top or bottom. You got an electron in this p orbital, you don't know where it's going to be, top or bottom. So this is 1 orbital, this is 1 orbital, and they share that electron. And the pi bond overlap. Now, that gives you 2 shared pairs. You got a sigma bond, which is say that bottom one, and a pi bond, let's just say it's the top one. In a triple bond, you're going to have 2 pi bonds. You're going to have 2 sets of p orbitals combining. See if I have a diagram of that. Okay, this one's all right. Here's an ethene molecule. So you have, there's your sigma bond, there's your pi bond. This is 1 bond, top and bottom, it's 1 bond. If you put them together, you have a sigma bond and a pi bond, and that's your double bond. Sigma's 1, pi is the other part of your double. In ethine, which is acetylene, you have, in ethene, you have hydrogen, hydrogen, carbon, carbon, hydrogen, hydrogen. In ethine, you have hydrogen, carbon, carbon, hydrogen. Well, the 1 hydrogen, they don't have this one drawn on here. I have to draw it like this. In other words, ethene is like so. Ethine is like this. Okay? This is acetylene, same thing used in acetylene torch. You have a sigma bond between hydrogen and carbon, and then, same thing on the other end, you have a sigma bond, let's say it's the middle one, right there. And then you got a pi bond, top and bottom. And the green one's a top pi bond, front and back. So you have a pi bond front and back, pi bond top and bottom, that's 2. And a sigma bond down the middle that you can't see, that's 3. Ugh. Okay, so bond length and strength are usually related. Shorter double and triple bonds are usually more energy involved. Double bond length and bond strength are typically related. The shorter the bond, usually the stronger it is. Double bonds are shorter than single bonds, so they're stronger. Triple bonds are shorter than that, so they're even stronger. Triple bonds are strongest, then double bonds, then single. N2 is a very good example of a stable molecule. It requires a lot of energy to break its triple bond. You know, nitrogen it's very stable. It doesn't react with things. To determine whether the reaction is endothermic or exothermic altogether, you have to consider the total energy of all the bonds broken added to all of the bonds formed. An endothermic reaction occurs when a greater amount of energy is required to break all the existing bonds than is released when new bonds are formed. And whenever you break bonds, you're going to make new ones. Take all the energy to break all of them and add it to all the energy when you get new ones. Which one's bigger? Exothermic release more energy when the new bonds form than was required to break all the bonds in the reactants. Let me back up one. Remember back here what I was talking about? Acetylene, very high energy fuel. Well, that's because not only because there's 3 bonds here, it takes a lot of energy to break those 3 bonds. But when you break those bonds, you get new ones with carbon dioxide and water, and you get a lot more energy out of those. So when you add all the sum total of all your input and all your output, you invest a lot of energy to break these, but you get a huge amount of return. This is very exothermic. Kind of your reasoning is because you have triple bonds. Now look at this. When you have N2, this is very endothermic because you have triple bonds. You have to input a lot of energy into this, but you don't get the payout when you make new bonds with other things. The amount of energy you get out of those other new bonds isn't as much as you have to input here. But in both cases, you're at an extreme because you have a triple bond. Okay, we'll stop there.